Chapter 10. We're going to start with radical expressions and functions, and they're going to do a couple things to make sure that they have a function, and we'll talk about that as that comes up. But the first thing we're going to talk about is these radical expressions are with roots, what they call it, which are kind of like the opposite of an exponent, though that's not real proper terminology. Um, they're really kind of more of an inverse function in the sense of when we talk about exponents and stuff like that. And this chapter will go through a lot of different ways to deal with these radicals, and eventually we'll get to how to express them with just um, as an exponent and so on, and we'll find some shortcuts. But first, let's talk about what these things are. The first two things they talk about are square roots and square root functions, and and it says when a number is multiplied by itself, or squared, um, if we can find the number that is squared in order to produce the value of a, that is called finding the square root. So in the square here, it says square root is a number c is the square root of a if c squared equals a. In other words, if I had this c value and I took the square root of it, the answer, the square root, would be a, and so on. If we look at examples here, 9 has negative 3 and 3 as square roots because negative 3 to the 2 power squared. That comes from the area of a square. You take side times side, ends up being to the 2 power. That's where that nickname of being squared comes from. Well, negative 3, squared is 9, and so is 3 squared is equal to 9, and so on. So these are roots, square roots of 9 are negative 3 and 3. So they're going to set up some examples of looking for the two square roots of 36, which are 6 and negative 6. And the way to prove that is that if you squared those two numbers, you'd get the same result of 36. Now they're going to bring in this idea of a principal square root, and it mostly there's something that happens with the square root function that makes it not a function if we allow these positive and negative answers to a single number. In other words, we got a domain issue. If we have two x values for one y value, or f of x value, and there's two actual x values that give you the same thing, that makes it not a function. It's not within the definition of a function. And then if we, going back to some prior chapters, if we graph that, you have that vertical line test on a graph of any kind of expression or equation, and we can test to see if it's function. And how you do that, if you create a vertical line and it crosses that graph in two places, that means that there's two x values or two horizontal values for one vertical value. So, which has some function deals. Well, with square roots, when we have this issue with the positive and negative, we're going to define, or basically take, a principal square root, which is the positive or the absolute value of the root of anything in a radical sign, okay, with square roots. So we have a principal square root, and what they do, and why they're doing that, is then we can get a function out of this thing, so we can apply our function rules to these square roots. So when they're talking about principal square roots, like the square root of 25, there really are two roots, but when we're talking about principal square root, we're talking about the positive value. And so this symbol indicates a principal square root as far as this book is going. So when we see this square root symbol, we're going to be talking about the absolute value of this numbers that we could square to get 25. So in this case, the answer would be 5, and negative 5 is not an answer. So they give us some different examples with rationals, and you got to remember too, if I have a negative outside of this radical expression, this square root in this case, like here in example C, that means that you're going to take order of operations as you take the square root and then take the negative of that. So we take the square root of 64, which is 8, and the negative of 8 is a negative 8. So they go through, we should be able to deal with complex fractions now and those kinds of things. And here's a graph of principal square roots with this square root symbol. And you end up with this half of a parabola that's sideways. And we were talking about that vertical line test. Well, when I'm talking about principal square roots, there is actually only one x value for every y value. So, but if I didn't have a principal square root and I said that f of x squared equals x, I would end up with this and this kind of thing, or it would be not a function, or y squared equals x would be a better way to say that. I'd end up with the other half of this parabola down here, if you see where the hand is kind of going across here. Well, if I did a vertical line test, I'd get two values for my x, and I'd not have a function. So by taking this principal square root, we basically are making this a function, where it has a endpoint really, but it goes on forever in this direction. But in this case, this graph here would include 0. So 0, 0 is part of that. If I describe the range of this function, it would be 0, everything greater than or equal to 0. So it does include 0 and then everything greater and equal to that. Okay. So I'll kind of review some other stuff to get some of the language in here. And that's what they show us here. The domain of this is this square bracket here again means that it includes 0, and in infinity or positive infinity, meaning to indicate which side it goes to. And then they use this non-inclusive part basically to say there's really no way to end point this, but it's kind of, they got to do it one way or the other. So they say from 0 to infinity is a domain, and also the range is 0 to infinity. This keeps on going gradually up, so as we keep going, the y values go to infinity too. Okay. Good review of what domain and range are in this case. Okay. So example 3 here, it says for each function find the indicated function value. So they have this function f of x equals the square root of 3x minus 2. And they want to know what f of 1 is. In other words, they're going to put 1 in for x and find out what this expression will end up being. Okay, and that's what they show us here. The solution is we'd put 1 in for x, and we'd end up with 3 times 1 minus 2, or we'd get the square root of 1, which is 1. Remember, it's not negative 1 because of this principal square root. The other example here, they got g of 3. In this case, it's a different expression they substituted in. And in this case, because if there's not a perfect square root under this thing, we end up with a non-rational number. In other words, a number that we cannot express as a fraction of 2 integers. That's the definition of rational. So we're going to end up with an approximation here. They take this and say, well, it's about equal to a negative 4.69041576, probably what the calculator would show on your calculator when you took the square root of 22. And then remember, you got to have the negative of it. So it could be 7, 5, 8, or something after that. So this is just an approximation, and which would be fine probably when we're going to get into irrational numbers or non-rational numbers. We're in the real number set, which is all rationals and all irrational numbers. Okay, expressions of the form of the square root of a squared. So we're going to look at this and we're going to find a lot of shortcuts to deal with ways to do that. And a lot of times we're going to want to not go to approximations. We want to go to a simplified form, but we're going to leave the approximation in its smallest, simplest radical form eventually. So, and that's coming up in this chapter. So in this case, where we have the square root of 5 squared, which is kind of like order of operations in a sense. If, when we're going to learn some rules to bypass that or work around order of operations, I have to square 5, I get 25, and then take the square root of that is 5. 0 squared is 0, the square root of 0 is 0, so on. Now in this case, if I had a negative 5 in here, I do square that first, which gives me positive 25, so I get the same solution of as 5, because a lot of it has to do with this principal square root thing. Okay. So simplifying, they're going to give us this rule that works for all values that could be in these radical symbols, or square roots in this case. So they're saying the square root of a squared is equal to the absolute value of a. Notice we had a negative and a positive 5 they put in. We always came out with the positive 5, or the absolute value of 5 is 5, the absolute value of negative 5 is 5. Okay? So we use absolute value signs unless we know that the expression being squared is non-negative, though they could still do that. Okay? Okay? Example 5, in this case they're going to be able to take this out. Now this is going to make a big difference especially when you get into equations again, is that we have real specific ways we have to deal with absolute values. So this will become very important when we get into equations. First they're talking about technique or simplifying expressions, and then we're going to get to equations. So like B here, if I have the square root of the quantity x plus 1 squared, this radical would take out that square, and then you'd have the absolute value of x plus 1. Okay. So if this was equal to something, then we'd end up with the absolute values equal to something, and then we have to deal with that, what could happen in this absolute value, which is you could have x plus 1 equal to something, or the negative of that entire thing, which is negative 1, or negative x, minus 1 would be the opposite of that, so on. So pretty important to note here, this absolute value deal we've had in last chapter, we were working with dealing with how do I solve things with absolute values in it. So they show a lot of different examples here of how that would come out. Now I left these icon deals here. Usually I don't leave these on during lectures. If I press this button here, when I'm on the interactive book, this is a very nice feature in here, and I probably talked about this before, but I can click on this and there'll be an animation talking about something similar to example 6 here, and there's a person talking, and you'll get something very similar to what you're hearing with me, and a little more rehearsed probably, and but it could have a different method of talking about it, which could be just the thing you need to hear. If you're an auditory learner, that's a very good tool that you can pull that up anytime you want, especially when you're working on your your homework. So we go through some examples here, and let's look at this example 6 stuff here. It says simplify each expression. Assume that the expressions being squared are non-negative. That's a big part of this deal, because what they did is say, hey, let's just avoid the absolute value thing for now. We want to work specifically on how do I simplify these expressions. And here we go with factoring here if you look at example C. And let's go to that one directly. Now they're assuming we don't have negative issues, so we're not seeing those absolute value symbols. But only do that if they give you instructions to take care of that, because that is an issue that we'll have to deal with over and over again. So let's look at C here. We got the square root of this polynomial here, this trinomial, of 9x squared minus 6x plus 1. And what they did is they factored that again. There's that factoring stuff coming back. And they recognize that this is a binomial squared. Is 9x squared something squared? Yeah. And then I check this last term, it's 1 something squared. So I got the possibility of this being a binomial squared. I think about what the terms would be. To get 9x squared, I'd have to have 3x's, one of the terms in the binomial. And to get 1 squared, I got to have 1. So 3x times 1 is that, and I double that, I get 6x. So this is a binomial squared, and then this is a negative, so I know that this one has to be a negative. And if you can recognize that in factoring, it's going to save you a lot of time. So try to use those recognition tools for factoring. If not, you can still use anti-FOIL. It just takes more time. But now I have the square root of something squared. Now we're talking about what they gave us for rules here. So I can take the part that's squared and take it out, and I end up with just 3x minus 1. And again, they say assuming that 3x minus 1 is positive. It doesn't end up to be negative. That's the assumption going on here. So make sure that we address all possibilities. If they wouldn't have said that, we'd have to have at the end of this say it's actually the absolute value of 3x minus 1. Okay, cube roots are very similar. Now we're talking about cubes are that nickname for to the third power comes from if we have a cube, an actual cube, and we want volume, you take side times side times side, or it'd be s to the 3 power would be the volume. So, and that's where the word cube comes for to the third power. And they remind you, they show you some examples of what that means. 2 is the cube root of 8 because 2 cubed, 2 to the third power equals 2 times 2 times 2, or 8. Okay, and so on. So now they're going to tell us that cube root is of A is C if C cubed is equal to A. In other words, to put this kind of in the terminology, it would say that 2 is the cube root of 8 because 2 cubed is equal to 8. Okay? So in symbols, and this is how you show a cube root, you put a little 3 there into the radical symbol right there, which is used. You just have it for square root, and square root is probably the most used one, so they don't put a 2 there all the time, just like you don't put a 1 exponent. So if there's 3, and then you can have 4th root, 5th root, and so on of that pattern. But if there's a 3 there, it means cube root. So for every real number, we do this. Now we don't have to deal with this positive value where they're talking about. Let's just deal with the positive roots, because it is an odd power. We can have negative range values here, because like -2 has a unique cube. It has a -8 as its cube, where 2 is 8. So there's a sign issue. Having an odd power means the result of cubing will maintain a power that makes it unique. In other words, we don't have to redefine cube roots at all to make sure that we stay within a function. This is a function again because if I draw a vertical line here, there's no two f of x values for any range value or x value in this case. Okay, so this is a function without having to redefine or limit parts of it to make sure that it stays function. So for each function here, find the indicated value of the function here. We're going to substitute things in for y. It says f of y equals the cube root of y is how you'd read this. Well, if I put 125 in for y, in other words, what is the cube root of 125? Or what number times itself 3 times equals 125? That means to the third power. Where this function here, g of x, equals the cube root of x minus 1. They want us to find what happens when the x is -26. So g of a -26 equals the cube root of a -26 minus 1. So we get the cube root of a -27, which is -3 cubed is that, okay? So the cube root is -3. Yes, signs do make a difference, okay? Signs are a big deal, so don't think that having sign errors is not a problem. It comes to haunt you in a lot of different ways. Well, in this case, this example 8, we have the cube root of a -8 y cubed, and which is -2y cubed. Okay, so this cube root is a -2y. Now let's look at odd and even nth roots. The fourth root of a number is a number c for which c to the fourth is a. The fifth root and sixth roots and so on, we write that as that radical symbol with the n there, where we used to have the 3 and so on. So they're going to talk about that we're going to write for the principal nth root, okay, is called the index, or the number n is called the index, or plural indices. When the index is 2, we do not write it because that's probably the most common root we try to get as square root, so just to save some ink, I guess. So when the index is odd, we're taking an odd root. Well, again, because of this function issue stuff, they're going to distinguish between the two. Every number has exactly one real root when n is odd. So in other words, it stays a function. I have a unique f of x for every x. Okay. Now odd roots of positive numbers end up positive, and odd roots of negative numbers are negative. Now absolute value signs are not appropriate when finding odd roots. Okay. In fact, it will indicate or cause a non-solution, really, when we're talking about equations. So here we're looking for the fifth root of 32, and which is 2, which 2 to the fifth power is equal to 32. Where the fifth root here, example B, is the fifth root of -32, which is -2 to the fifth power equals -32, so -2, and so on. And then they go, hey, all these first 4 examples are just dealing like, hey, look, when we have different negatives in different places, what happens? Make sure you follow order of operations. Well, this next thing that can happen with the index, or the type of root it is if it's even, we end up with one positive and one negative root. Well, negative numbers do not have real nth roots when n is even. When n is even, the notation indicates a non-negative nth root. Thus, we simply even nth roots. When we simplify nth roots that are even, absolute value symbols are often required. And again, this is to stay within our definitions of functions because we're going to work with functions quite a bit. So this box gives nice examples of what those two things were explaining. If I have the cube root of 8, that's 2. If I have the cube root of negative 8, it is negative 2. Okay? So they have unique range values that come out of these functions. Where even roots, if I have the fourth root of 16, it's equal to 2. And I could also say possibly that I could take negative 2 to the 4 power and get 16. But we're going to say we're going to take the absolute value of the root, which is going to be that positive 2. And also we got an issue with even roots. If there is a negative number under here, there is no real solution, no real root to this, or no real number root. And the reason they say it's no real, in fact, we're going to have another number set at some point called the imaginary numbers, where they're going to deal with even roots of negative numbers and so on. And then if we do have this indication where we have a variable, then we're going to still deal with this absolute value, because we usually are going to want to represent all solutions when it's in that form. So they give us some examples of how that goes through this stuff, and here's that domain deal that I talked about a little bit. If g of x is equal to the sixth root, an even root, right, of 7 minus 3x, since the index is 7, the radicand, which is the part under the radical of 7 minus 3x, must be non-negative, or we're going to have an issue with staying in the real number set. So what they do here, they say, well, make this radicand, or this part under here, greater than or equal to 0, and then solve that for x to find out basically what values of x will work in here. In other words, I'm determining what range values will work. Okay? So they express the domain here in set builder notation, or here is the interval deals. So good luck with the assignment, and 10-2, and I think in a lot of ways this chapter will be a lot of review, and hopefully a chance to have an easier chapter. We're kind of introducing some old math, but in some new ways to deal with functions. So